Hello, this is John Golden from GVSU, and I'm here to do a couple problems for the Professional Readiness Exam math preparation. So we have a problem here from Tulip. It's a geometry problem, references a classic construction. So when I do these problems, I'm not so much telling you how to do them as trying to do a think aloud. So to share how I think about it. What do I do when I read the problem? In the figure below, ray EF was constructed from rays ED and EG. So rays mean just they have a start and then they go off in one direction. By using a compass, D and G were marked equidistant from E on rays ED and EG. Okay, so I can look at the problem and find what they're talking about. So we're starting with E and these two rays, and then we're adding. So sometimes I even like to redraw the problem. So we've got a ray and another ray, and at this point E. Okay, and we're marking 2 points. So we have a compass that's like a circle. So we get a point D over here, and F. And the idea is if we marked them off with a circle, they're the same distance. So I'm going to put a little bar to indicate those are the same distance. The compass was then used to locate a point F distinct from E so that F is equidistant from D and G. So we don't know it's the same distance, but we're going to find some point that's the same distance from D and F, but that might not be this distance we used before. So say we have some really long circle and we mark it off, and then we keep that same distance and we mark it off. We'll get a new point F. A new point ED and EG. Oh, okay. So keeping clear which point is labeled which. So we've got this new point F. We're imagining that ray. What we know is that this distance and this distance are the same. And so what they're asking then is about angles DEF, so this angle, and this angle, GEF. Okay, so individual question, are they equal? Well, obviously I can't go by my picture. In this picture they look equal. They're not equal. Some to 30, some to 45, some to 60. So right away, just thinking test-wise, I don't have any angle measures. I could have started off with a really wide ray, a really wide angle. I could have started off with a super skinny one. So they're getting you to try to look at this and estimate what the angles are. So I'm going to eliminate these answers immediately. So what this question's really asking is, are they equal or are they not equal measure? So, and what we know is we've got this pair of equal sides, this pair of equal sides. So one of the main ways in geometry we show angles to be equal is to use triangles, because we know so much about triangles. So in this case, if we look at triangle DEF and triangle EFG, they have a lot in common. They've got this distance the same, they've got this distance the same, and then they share a side. So this length in the middle, that's the same for both of those too. So in fact, what's true is that this triangle EDF is congruent to triangle. Now here they try to put the points in corresponding. So E is the same in both of them. And we do the short side. So the short side takes us to G. And then F is the same for both of them. So that kind of helps us write it down in a way that we can see all the relationships. In particular, if these two are congruent, that means the corresponding angles are congruent. So their measures are equal. So this angle is equal to that one, and this angle is equal to that one. So the answer has got to be 6 here. Okay. Then just to check, with these problems, it's a little hard to check. We can't go back and plug something in. But just looking it over, so we start with ED and EG. D and G are equal distance. F equal distance from D and G. Okay. I'm pretty sure this one's set. Okay. So a second problem I brought with me is what's called an angle chasing problem. So right there. Okay. So in this one, the question was, what is angle alpha? And it could be called anything. It probably won't. They won't use Greek letters too much on the test. It's a tradition because these problems came from the ancient Greeks originally, from Euclid. Okay, so in this one we're given this one angle, and then we're given some equal distances. So on first glance, it doesn't look like we even have enough information about this one. So with a problem like this, I just try to think about starting with what I know. So I know, going from the markings, that these distances are equal, and this distance is equal. Okay, well, so that means these are isosceles triangles, little CDE and BDF. So isosceles triangles, what do I know about their angles? I know their angles are congruent. So this angle is the same as that one. They're base angles. And this angle is the same as this one, but they don't have to be equal. In fact, you can see in the picture they kind of don't look equal. What else do we know? Oh, well, we know something about the angle B and angle C, just from that they're in a triangle, right? So angle A plus angle B plus angle C is 180 degrees. And then, oh, well, we kind of know, so let's call this one angle E, just to keep the names a little shorter, and angle F. Okay, so this is the same as angle E. So I also know angle E plus that copy of angle E plus angle C is 180 degrees. And I know that angle F plus another copy of angle F plus angle B equals 180 degrees. All right, so angle A, B, and C, angle F, 2 copies, and B, E, 2 copies, and D. Angle, I don't have anything about angle alpha yet. Wow, but these three together make up a straight line, which is another 180 degrees. So angle alpha plus, I was calling that angle F, and this one, which I was calling angle E, add up to 180 degrees. Okay, so this is going to be my best way to find angle alpha. That's the only thing I really know about it. So I'm going to rewrite this one. So angle alpha is equal to 180 degrees minus angle F minus angle E. So if I could just find that F and E somewhere, I'd be set. Okay, and angle A, I know it's got this value. So I want to remember that that is not an unknown like these other things. So angle, so I could figure this out, right? So angle B plus angle C, I know. That's going to be 180 degrees minus this angle A, which I know. But I don't have anything with B and C except these two separate ones. I could combine them. So if I add these two together, I'm going to get 2 of those angle E's plus 2 of the angle F's plus angle B plus angle C. That's all adding up this left side is going to be equal to 180 plus 180, 360 degrees. So angle B plus angle C is equal to 360 degrees minus the 2 angle E's minus the 2 angle F's. Okay. I'm going to lose the picture just to get some more space to write. Okay. So I've got angle B and angle C is 180 degrees. F and E. Here's my equation with F and E. Oh, look, kind of the minus is the same thing again. Let me rewrite that a little nicer. Angle B plus angle C is equal to 360 degrees minus 2 angle E minus 2 angle F. Oh, look at this connection. This side is exactly double that side. Okay, so if I divide through this whole thing by 2, which is really dividing both sides of the equation by 2. So I get angle B plus angle C, half of that, is equal to 180 degrees minus half of this, which is angle E, minus half of this, which is angle F. So that means alpha is equal to half of this angle B plus angle C. I've got this, and I'm going to substitute in this overside here. And that helps because angle B plus angle C, I know what that is. That's this 180 degrees minus angle A divided by 2. So this solves it in general, but the problem, this will be messy, is asking for what is the angle. Angle A we said was 45.01 degrees. So over here, 180 degrees minus 45.01 degrees. Totally okay to use a calculator, especially in a test situation. So 180 minus 45, 180 minus 40 is 140, minus another 5. That's 135 degrees. But I also have to subtract off this 0.01. So I'm going to say 134.99 divided by 2. And half of 120, 60. Half of 14 is 7. Half of 99 hundredths is 49 hundredths. That'd be 98. And then I need an extra 5 thousandths. Yikes. Okay. But you're doing that on a calculator, I hope. All right. So here we've got our answer, 67.495 degrees. And it doesn't say so, but this is an accurate diagram. It looks about right. What's interesting is it doesn't matter where point D was. All it mattered was that these things were were isosceles triangles. That's all we used there. So there we've got a pretty complicated angle chasing problem. All right. And from this one, I think about the problem-solving strategy is I didn't really know how to solve it to start, but I just took what I knew and kept looking for connections. You know, what did I know? I knew about the distances. That told me isosceles triangles, and I knew I wanted something about angles, so then I looked for angles. And that led me forward to where I could look for connections. So there's connections between the information. That's pretty good. This is a challenging problem. All right, and that's it for this problem session. Thanks very much. Please suggest more problems. I'm very happy to do them. Thank you.